All right, afternoon everyone. I'm here with my colleague Ari Flink. We are going to present preventive maintenance in automotive industry. Quick intro about, actually the agenda is next. So we're going to be talking about the IoT evolution, a bit about big data, and also about Cisco Cloud Platform. And we're going to deep dive into a case study that we have implemented recently for one of the robotics industry, and also into predictive maintenance and what it means. Harry, you want to?
All right, yeah. Hello, everybody. My name is Ari Flink. Let me do a little fun fact about me first. So I'm from Kemi, Finland, and what's fun about this place is that at this time sun doesn't set. There's 24-hour sunshine. So that's the good news. So the opposite is that in the winter time there's no sunshine. And if I can get forward, so well, what people came up. So we are building a huge snow castle in a town. People come to see it all over the place, all over the world actually, which is pretty good innovation. This has been going on for 20 years now. So Kemi, Finland, your next destination. Let's see. And in my day job is I work as a solutions architect at Cisco Cloud Services, and I design how to deploy services on a platform like big data as a service, database as a service, business support systems and things like that. Previously, I was working mainly in operations area in WebEx and eBay, ensuring operational readiness for complex distributed services, such as like WebEx meetings and various eBay components. And so I did a lot of DR, HA, configuration, deployment, monitoring, things like that. And so I'm from the cold climate, and my buddy here is the opposite. So do you want to say something about yourself?
Yeah, definitely. Just opposite of Harry, I like the heat, and one of the cool facts about me is that I love, if only I can get to the next slide, I love to do Bikram. That's kind of where I hang out most of the weekends. And I'm not as flexible as the guy in the picture, but hopefully I'll get there someday. The other passion I have is I've been into big data for the last 4 or 5 years, and it's been quite a journey. I've learned a lot, and hopefully I've contributed quite a bit to the industry as well. Previously to Cisco, I was at a couple of other companies doing distributed systems. I've been working mostly with large data sets last few years, sometimes even petabyte scale data. A quick intro about Cisco Cloud Platform. It's not well known, it's not as publicized, but we did go live a few months back. That was version 1.0. And there's another version 2.0 coming up. We are using most of the open source platforms out there: OpenStack, Cloud Foundry, Docker, Kafka, Hadoop, and even Cassandra for some of the infrastructure related items. Right now it's mostly internal facing. Most of the internal customers are Cisco groups itself. And as things mature, we are going to be leveraging it and making it more publicly available. Let's see if I can get that. So yeah, that was talk about us. We wanted to know a bit about you guys as well. If you can have a show of hands, who all are from big data space or are interested in the big data. It's about 15. What about robotics and car manufacturer? That's pretty good. What about IoT? Of course, this is the IoT track, so cool. Okay, that's pretty good. So we want to talk a bit about the IoT evolution, how it came to be, and it will help us understand where we are at right now. So the computing eras can be divided into 4. It started out with the mainframe and then went into PC and web. We can see a few icons which are there and which are not there anymore: Explorer, AOL, Netscape. Then we went into cloud and mobile, which is what has been around for some time, with the cloud computing coming up. And then more recently, I can get this to go.
Slow clicker.
There we go. IoT. So that's kind of the more recent, I would say, era in computing. And the IoT platform that we have right now was made possible by the big data space that's out there, the mobile, the cloud. We could not have done IoT maybe 20 years back because a couple of reasons. They didn't have the software, the languages to go with it. Neither did we have the cheap infrastructure that enables IoT. And as these became more cheaper and more readily available, it is now commonplace to think about IoT as something that is going to be there and probably something evolving after that. So with this, I give my talk to
Yeah, so this
Frank.
is the motivational part here. So why is preventative maintenance for robots such a big deal? And so here's a clue. So how much does unplanned downtime cost a car manufacturer? Does anybody happen to know the answer? Amit, what do you think?
I know the answer.
All right, it's 20K per minute. That's the average outage for in a car plant. That comes to 1.2 million per hour. How about the single incident? What about that?
A couple of millions.
2 millions. Right answer. So you know the answer.
Yeah.
Anyway, so it's a big deal when things go wrong in a plant. So $1 million question is that what robot will fail next and how can we predict failure? So this is the topic of the talk today. Let's go back a little bit if I can go forward. So this is where it all started, like Henry Ford invented the assembly line. And back in the day, and a lot later, the main goal was to keep the line moving. So you wouldn't stop the line. And in the past, because there was no robots, I guess it was easy to replace people. So line kept moving and cars were produced. So coming to present day, things are a little bit more complicated. And the lines are very, very high volume. They can crank out the car one per minute. And if a line goes down, it's a big deal in some cases. So the question is that why does a single robot failure matter? Why is it a big deal?
Looking at me. It's probably because there is no high availability, there is no redundancy,
Yeah.
and also, there is, if it fails, it fails. There is no backup, right?
Right. So if a robot fails, the whole line stops. So there's no high availability there. There's not another robot taking over. So the robots are very reliable. Like mean time between failure is something like nine years. So it's not that they are breaking all the time, but when they do break unscheduled, then that's the problem here. So the solution that Cisco and Fanuc have cooperated is called zero downtime. So it analyzes data coming from robots and controllers, gets the data in the cloud, and there's some algorithms that can detect when the failures are about to happen. So this is currently in production for 6,000 robots, and GM alone has deployed to 27 factories in 5 countries, covering 5,000 robots. And it's been very successful. It's a very small scale, relatively small scale at the time, but it has detected many cases and saved 40 million for the customers already. So very, very successful start for the program. So I'm going to talk about the initial pilot program, like what is it made of. Go a little bit more into detail next. So overview of the flow. So here's your production line, and you got your robot arms and your controllers working in a factory, cranking out car per minute. And they send telemetry to the local plant data collector. So this has been a problem in the past because there hasn't been any connection from the plant to the cloud. So everything's happening within a cell in a factory. With this system, we can send the data securely to Cisco Cloud, where it's analyzed for out-of-range conditions, and the system can schedule parts to be delivered to the plant, and schedule the maintenance people to do the repair during the regular maintenance window, and you can avoid the big outages. So the robots typically work like 2 shifts, 2 times 11 hours. So they are working 22 hours a day. So there's a window for maintenance, but you just have to get to the maintenance at the right time. So that's the whole idea here. So getting a little bit deeper in the data flow. So we have manufacturers who have many plants, and in a plant, the robots talk to each other within the cell, but they haven't been able to talk to the outside world. And this is where the programs come. There's a thing called Cisco IoT platform. It was previously called DXM or something like that, but now it's called Cisco IoT platform. So this is the interface to outside world. So it abstracts the robots from the data, so it can be used for not just these robots, but other kind of IoT endpoints. And the pattern is replicated with multiple manufacturers, so this is a multi-tenant solution. From the Cisco IoT platform on-prem, the data is sent to Cisco Cloud, where there's another component that receives it in a secure way, and it's stored in a Cisco database as a service. This is a cluster where the data is stored, and the applications run on this data and do reporting, analytics, notifications to the car manufacturers. Oh, my thing doesn't work. Oh, all right. and the equipment provider. So here's the high-level view. And so the way we went doing the architecture a couple of years ago, in the Cisco Cloud, so there's a typical batch process from data ingest to batch layer to batch view to a serving layer. So this was your typical Lambda architecture that was very popular a couple of years back. In this application, the speed layer is not that important because this is really batch work, so it schedules maintenance for like next week. Like today, you might find out that there are 3 or 2 robots that needs to be serviced this week. So it's not like a real-time alarming system at this point, but there's a lot of potential for that as well. So just kind of filling in those boxes a little bit. So the data ingest it's received by Cisco IoT platform, from where it's going to Kafka. And the reason why this Cisco IoT platform is here is that at the time, Kafka didn't have the security. So it was meant to ensure that the communication is secure. Now, maybe it could be done without the IoT, but it's there. And from there, data is moved by Flume to HDFS, and there's some conversion like from XML to Avra at this point. And it's really simple, kind of basic from a big data point of view. It's just some peak and hive ETL that transforms the data to servable data with Impala. So the interface is Impala SQL, and the API is connected to that from outside. Real time is in a POC phase, and it's, if I can, there it goes. Spark streaming and A-Space. So pretty basic from like a big data point of view. There's now no magic here, but it's still been very, very successful for the customers to detect failures that are about to happen. Let's see, there's another layer. Go there. The UIs are going via API, and the API layer provides the multi-tenancy here, and the backend is there. So you have to kind of move your hand.
It likes animation.
Yeah, right. So that's kind of like high-level detail of the pilot program, the way it's implemented right now. So in summary, it's batch mainly, collecting data from multiple vendors, multiple car manufacturers, multiple plants, global system, secure, runs in the Cisco cloud. And Amit's going to take it from here and go to the next phase.
Sure.
Move your hand when you...
Yeah, I'll try. So what I talked about was a preventative maintenance model, and that's a pilot program that's implemented. The next, I would like to say in the evolution cycle is predictive-based maintenance, predictive maintenance platform. Here the idea is obviously we have issues about high volume and production loss if things go south, if there's a robot that fails, right? The key there is that we want to do the maintenance and also any uptime and downtime kind of scheduled or unscheduled maintenances at the right time, right? Not too early, not too late, just in time maintenance. And for that, we need a self-monitoring, self-learning system, which will be able to understand and based on feedback that it gets back, right? So if a maintenance, for example, was scheduled for 2.5 months, for some certain model, maybe a few months, or in a different plant, it takes 2.4 months. So what is the average of that, and how do we learn from that, right? So every event that happens is going to be a feedback into the system to increase the knowledge base of what is the normal average time. And based on that, be able to kind of proactively react to it versus waiting for something to fail or sending somebody too early or sending a part too early. So this curve kind of summarizes what we are trying to get to is the sweet spot, which is this is a typical bell curve with any metric on the y-axis and time on the x-axis, right? And we have a sweet spot of about 2 standard deviations, which is where most of the data sets is going to lie. So as long as we are able to handle that situation, we should be fine. Anything before that is too early to maintain, and anything beyond that is going to be too late, right? It's going to be very expensive. So how do we, so here's another view of what Ari already showed. In here, we can see that there is no human touch, right? So as soon as the data is loaded from the factories over to the cloud platform, the data is crunched through and also notifications sent. And there is no human intervention required because it's all based on metrics and it's a self-learning platform. And if there is a maintenance that needs to happen, the email is sent out to the car manufacturer and also the robotics company to send the parts that is required by FedEx, and also the tracking number is mailed and shipped to the factory to expect it. So the 3-day lag time for the shipment and all of that can be handled up front and baked into the scheduled maintenance, the routine of that, right? So this way we have almost zero downtime, and that is kind of the goal with the predictive maintenance. Here's a quick graph of where we are right now, which is on the reporting side. So the pilot program basically tells about what happened at a certain time, and where we want to go is on the right side of this progress bar, which is to go to predict and figure out what might happen, and based on that, what is the action that we can take. And as we go from left to right, the return on investment is going to go up, but so does the complexity, right? You have to deal with a lot more data, with a lot more decision points, and a more complex platform. So here's a bit intro about how the data modeling might happen for preventative maintenance. We have to define the problem. So on the left side, we come up with the initial data set, and then we have a validation layer, which is testing the model out that we think is the way it works. And then we apply it to production. And based on that, there's a feedback loop from the green bar back to the blue bar area, wherein if things don't work the way we expect them to work, we are going to feedback and say this is the delta, right? It's like a self-learning algorithm. Here is a platform that is Kafka based, Kafka and Spark based, which might be able to solve a predictive analytics platform. This is a proposed architecture. It's not implemented yet, but it's still in the works. We're going to still use the data ingest layer, which is from the previous version in the pilot, having the IoT platform, the Kafka. And then we're going to have a stream processing layer, which is where the data is stored as raw data sets in HDFS and then ingested into Spark in memory. And with micro batching, it's able to process the data. So we have the stream processing layer and then the learning layer, which is the Spark ML platform, right? That is where kind of the brain or the learning system is, which is basically observing the stream processing layer as it is acting on events. And is there something to learn on the model that it already has, right? Was it an anomaly, or was it an event that happens in the 1 or 2 sigma that is out there, right? So all of that data gets fed into the Spark ML platform, which is machine learning, and then that updates the knowledge base. And each of these knowledge base elements are fed back into the stream processing layer to do the decision points, to make the decisions, right? So once a decision has been made, we have a separate action layer, which is where the action happens, which is what is based on a certain event. It might be tagged as a maintenance, or someone needs to go to the plant to go fix something, or a part needs to be shipped, or maybe it's just a monitoring or dashboarding kind of an app, right? So this platform can be either custom built or Sensu based. Now Sensu is a single pane of glass concept that has come up, which is heavily used nowadays in the industry for monitoring the data centers and other kind of machines and stuff. So if you have a large data center with a lot of hardware and software loaded onto it, Sensu is a good dashboard based customizable platform which allows you to ingest data and create custom dashboards. Now PagerDuty is another product, commercial product. It has an open source version as well, which kind of has emails, pages, phone calls, you name it, and they have it, right? So any action that needs to happen can be sent to PagerDuty platform, so to speak, and then they will further downstream it. So yeah, at this point I would like to double click on the stream processing layer and the learning layer, which is the, I like to say, the heart of the engine. This is where the actual thinking and the brains is, right? The left is the data ingest, which is the ingestion layer, and the right side is basically the action part, right? So in terms of data storage formats, there's a couple out there. There's Avro, there's Parquet, there's ORC, and of course the original text-based. So this is kind of a quick comparison, right? If the data is huge and we need compression, ORC is a good format. The only thing with ORC is that it works very well with Hive, Hive 2.0 and any version of Hive. Parquet is much more efficient, much less efficient. Okay, sorry. Should have muted this. Sorry, guys. Yeah, so Avro is a raw format based file storage. What it does is that it's going to store data contiguously. So if you want to load data one row at a time and you feel like you have to work with all the data sets within the same row, then Avro is the right format. Parquet is column based, so if you have a subset of columns to work off of versus the entire column set, that would be Parquet or ORC. Now Parquet and ORC have similar column based usage, but the difference is Parquet is used heavily with Impala and ORC is used with Hive. In terms of implementing Spark on Hadoop, this is kind of the subset of what we would want to implement on a Hadoop platform. We have the file system as DFS based, and we have the workload management, which is Yarn, and then machine learning and stream processing are both Spark based, right? So this is kind of the implementation that both Hortonworks and even MapR to some extent and Cloudera are using right now. So we'll talk a bit more on the action layer. So on the action layer, we'll just double click. So here we get the events from the Predictive platform. So on the left, as you can see, right, so there are events that are coming in. So these events are tagged events. So they are already processed. And so an event would look like, yes, there is a friction increase or some kind of a torque that is outside the anomaly. We need to send a mechanic down to figure out what the problem is, right? Maybe that is what is the event. Or it could be a part that has stopped working and we need to replace it, right? So these are the events that kind of get fed into the event consumer. And there is an event store that stores it, and there are various implementations of the store that we can do. If it is, the data is up to maybe a couple of gigabytes, maybe tens and 20s of gigabytes, MySQL database should be fine. Whereas if the data is beyond a couple of terabytes, then obviously you have to go with a NoSQL, which is Cassandra or HBase. So data size does matter, but however, given that we have a dashboard on the right to perform ad hoc queries on, the response time needs to be super fast, right? So for that, either MySQL or a NoSQL database would be appropriate. And in terms of for downstream apps like PagerDuty or email app, there will be an API-based event topic. So it's going to be a pub-sub model, which is a publisher and a consumer. So that blue arrow and the blue box in the middle is going to be a pub-sub topic-based model, which will be able to have multiple subscribers to it. So some of them could be an email client or PagerDuty or any other that can consume from the event. On the right side, we have API for ad hoc queries. So if you go for any of the NoSQL implementations, then we would have to use a Solr indexer on top of it. So that's kind of the standard industry solution these days to implement any of these NoSQL implementations. We have a Solr indexer on top. What that does is it has this kind of hash map of maps, and it's able to very fast, if you give it a query, it's going to be able to execute the data and get the data out very fast versus reading through the data sets sequentially, right? So that's what happens in big data. So that would be a way to implement the ad hoc queries. So quick recap, right? So what we have been able to implement so far, if you use the predictive model, is that the outage, of course, is reduced. The other thing is there is a lot of talk about, even though the robots don't need to take a break, but there is some articles from CEOs of a lot of robotics companies that if they have, what they've found out is if they do instead of doing 2 12-hour shifts, if they do 2 11-hour shifts and give a 2-hour break in between, the robots are able to function better, because what happens is those mechanical parts, some of them overheat, even though they may not exceed the technical specification, but it does allow for the robots to, I don't know, think of it like a rest, right? So what happens is if we know the cycle of how often the robots needs to be replaced or some maintenance needs to be done on them, the breaks can be planned so that probably the downtime can be, the unscheduled maintenance can happen in the break time versus some time where they have to break the assembly line and do the full thing, right? So there's a lot of applications of an implementation like this wherein we are able to have a dashboard and have a schedule and have basically the latest and greatest information about what is happening to each robot, right? So with that, we open up to Q&A. And
yeah, I just want to say that,
if you want to add some more.
Yeah, the program is, right now is processing data for like 6,000 robots, but that's just a really small number. Like Fanuc alone has like a base of 250,000 robots out there, 2.5 million CNC machines, so there's huge upside, and so this is just a start, so it's been very successful so far. Yeah, go ahead, sir.
Yeah, so this is all well and good if you have network connectivity that can stream basically back to the cloud.
Yes.
To do all this type of activity, sometimes some of it in batch, some of it in streaming real time. But what's your future roadmap look like for do more streaming real time and to make decisions earlier rather than in the data center, closer to the edge?
Right, so that kind of reminds a little bit Cisco's fog computing. So that's the goal would be, of course, work at the edge as much as possible. But there's both use cases there. Like the use case what I was talking is really not real time.
Right.
So that can be batch and can be a daily job. But
you want to be able to see threats, problems of the robots as they're emerging and be able to react on them.
yeah, absolutely. So there's a lot of data that hasn't been used right now. But there's like troubleshooting data, tracing data, very valuable. One issue is that the plants are very protective about the controllers and robots because this can cause any other problems. So it's very slow deployment and very careful. But there's just tons of data that hasn't been used yet.
So any comments on what your roadmap may look like? I don't want you to announce
Yeah, so there are some downsides of decentralized. I think you're talking about decentralized decision making, right? So be able to make a decision right at the place where it happens versus uploading it to a central brain, whatever it is, let it crunch through and figure out what is really going on. The problem with a decentralized decision making model would be, the way I see it is like if you have something like a prediction based model, right, where you want to predict stuff there, typically you want to crunch on a large amounts of data. The more data there is, the better decision it's going to take. The problem is if it takes a decision at a small factory level, it might be a few thousand robots. It may not have the view and the global visibility of say 10,000 or 50,000 robots that's out there globally. So the economies of scale will not be there, and the decision making that is going to happen will probably be suboptimal. So that is kind of the risk. But of course, the reward is that, yeah, you don't have to wait, but hopefully with the high speed, data access and data transfer rates and Kafka, and I mean, each of these channels are constantly increasing the throughput, right? There's the data centers themselves, a while back they used to have 10G, Ethernet backbone. Now each of them is now 20G or 40G, InfiniBand and stuff, right? So the bandwidth, the capacity of each of these data centers has gone up quite a bit. So they can definitely move data much faster, much quicker to any part of the world and be able to process data almost real time.
So we got 3 questions right there,
yeah,
so
sure.
we can run out of time.
I don't know if I answered your question. We can definitely take it offline. Yeah.
Sir.
So you showed in your original diagram there the plant data connector. Can you talk a little bit about what that was and how you actually interfaced with it to get the data?
Oh, you mean from the plant to the
So the device that's actually talking to the controllers of the robots, what was that? How is it archiving data and how is it sending you the data?
Yeah, I don't have that information. I work on the cloud side, but it's basically there's the Cisco IoT platform that handles the connection to there's a Fanuc component that interfaces with the robots, and I have I don't have that information.
But then there's a controller that, I thought there was a controller that goes with a robot, right?
Sure.
And that robot, and the controller has a local, every factory has a local data collection agency or
Yes.
something, and from there it uploads to the,
What you ask in details, how?
What is that?
oh, okay, I see.
Just tell them that's CP and GSIM.
No.
Yeah, we don't have visibility on some of that, yes.
you guys had any like kind of aha moments? A lot of what you're talking about is like incremental improvements.
Yes.
But have you like plants in saltwater locales have higher mean time failure rates of certain parts, or certain providers of certain parts of the robots are less reliable than other providers, where you've actually made larger decisions where you're like, we're not going to buy parts from you anymore because your parts stink.
Yeah, no, that is where the Predictive platform, one of the usage of that would be, right, is, you know, if you're in a very salty environment, the same machine might actually start breaking much faster, right? So even though mean time between failures might be 9 years or 8 years, but it might so happen that it's 7.5 in some localities versus it might be 8 or 9 in some others. So that is where the learning part.
Holes in plants or things like that, or screw-on machines actually still outperform linear motors, or, you know, I mean, is there any, did you guys have you had any of those moments yet?
So that data is actually pretty proprietary. So the manufacturers don't want to disclose that what the findings are, because that's really their IP, their competitive advantage. Go ahead.
So you guys talked about a lot of anomaly detection. What was the experience around choice of algorithms that you had from the ML? I think ML is the future, right, for you guys?
Right.
Yes, that is the platform that we are trying to build towards.
What kind of challenges you faced from an anomaly detection perspective, and what worked from an algorithm's perspective and what did not? And did you ever face any issues with some of the algorithms overfitting and all that?
Yeah, we have curve fitting issues. Yeah, I mean, we are in the early phases.
What the kind of algorithms you
Yeah, so we are in the early phases of evaluating all the algorithms. So we still are kind of building up the platform, the Hadoop, ML, and all that stuff. So we aren't fully plugged into the robotics area, right? So it's more of a POC that is, we are, yeah. So it's more of a POC phase right now, and at some point we will get real data, and then we start to see which one fits better or not. So we are kind of still early on there. What is live right now is what Ari showed, is the preventative maintenance, which is kind of based on some heuristics which are, yeah, which is already fixed. Right.
Right.
Yeah.
I think we're getting the hook. Time's up. So we are happy to talk to you after the presentation.
Thanks a lot, everyone. It was very good having you.
Thank you.